Srimati R. Padmavati, Head of Department EC, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Electronics Honors for the subject Analog Electronics. Today we are going to learn about the different configurations of transistor as common base, common emitter and common collector, also its input output characteristics. So, in the previous lecture we have seen the circuit diagram of common base configuration in PNP as well as in NPN transistor. Also we have discussed some factors in output or collector characteristics of common base transistor. So, this is the output characteristics of common base. So, we have discussed about the cutoff region, saturation region and active region. In cutoff both the junctions are reverse biased and in saturation region both the junctions are forward biased. In active region the input junction is forward biased and output junction is reverse biased. So, if the base current is 0, according to the Kirchhoff's current law, IE is equal to IB plus IC. So, if the base current is negligible or 0, then the collector current is approximately equal to the emitter current in the active region. The input characteristics is shown here. So, this is the input characteristics of the common base transistor. So, this is similar to the forward biased diode, the input characteristics of the forward biased diode, and for the transistor it was plotted in between for IA along the y axis and VBE, that is the input voltage, the base emitter voltage along the x axis, the input current, the emitter current along the y axis for a constant output voltage, that is collector base voltage. So, this characteristics is similar to a forward biased diode. So, what we have done for the forward biased diode, the same way we are going to see. So, in this knee portion, knee region, we made line segments to approximate this curve, and so we obtained this piecewise linear characteristics using the line segments, and it starts from 0.7 volt. This is the potential difference across the depletion region, above which if we apply the input voltage, then the diode starts conducting. Here the transistor starts conducting, and again we have a slope in this curve. So, if the resistance effect is negligible, only because of the internal resistance of the diode we have a slope at its input characteristics. So, if it is negligible, then the slope will be ignored, and so it is a straight line here. So, this is the input characteristics of a transistor, which is plotted between the emitter current, input current and the input voltage, the base emitter voltage for a constant VCB, that is the output voltage, collector base voltage. So, what is said to be alpha? This is a parameter which relates the output current and the input current, or it is the ratio of the output current to the input current for the common base configuration, that is CB configuration. The output current is the collector current and input current is the base current. So, for DC analysis, if you derive the alpha DC, it is the ratio of the output current as collector current to the input current as emitter current. So, it is IC by IE, and we know that the collector current has two components, one is by the majority carriers and other one is by the minority carriers. So, the from this equation you can get IC is equal to alpha IE. You substitute here for the majority carriers. So, it will be alpha IE plus ICBO. It is ICBO in the sense collector base current when emitter is open. So, how will you imagine that current? So, it is a common base transistor where I have to give a arrow to represent a emitter. So, we know that input is the emitter terminal. So, it is the emitter terminal. If this is open, if emitter is open and this is the collector, this is the base terminals and this is the collector base current with emitter open. This is what given here for minority carrier flow. So, IC is written given as alpha IE plus ICBO, and this alpha it is normally 1 because almost the collector current is equal to the emitter current, but practically the value is taken as 0.9 to 0.998 because of some minimum value of current flowing through the base. For AC situations, alpha is given by the change in the collector current. It is the ratio of the change in the collector current to the change in the emitter current when the collector base voltage is constant. Almost for all the conditions, the DC alpha and AC alpha will be the same. Assuming IB equal to 0, if IB equal to 0, as I already told you, IC is approximately equal to IE. How it is happening in the circuit? So, this is the common base transistor. Base is common or it is grounded for which is in between the emitter and the collector. Emitter is the input terminal and collector is the output terminal, and the input junction is forward biased, output junction is reverse biased now. So, the emitter current is flowing to the collector through the base to the collector. We are assuming the base current as 0, and so it is flowing to the collector terminal. So, whatever the emitter current is in the circuit is almost all the current will flow through the collector terminal, and so the equation becomes IC is approximately equal to IE when we consider the base current as 0. This is the voltage amplifying action of the common base transistor, which is demonstrated with the small example here. It is the PNP transistor considered for the common base configuration. Base is common to the emitter and the collector terminal, and signal is given. The signal has the voltage 200 millivolts. The current is flowing through the terminal E and from the collector IL. The input current is II, the output current is IL, and the input resistance RL is considered to be 20 ohms. The output resistance is considered as 100 kilo ohms. Then the load resistance R is 5 kilo ohms. Now, the input voltage is 200 millivolts, and this is the example for explaining the amplifying action for the voltage. So, we have to see how this 200 millivolts is going to be amplified at its output. So, IL can be obtained by, this is II, the input current can be obtained by the input voltage by input resistance. So, input voltage is 200 millivolts by input resistance is 20 ohms. Finally, it is 10 milliamps. This is what the input current flowing through the emitter. So, if the current amplification factor or alpha, since this is the AC signal, alternating signal, the alpha AC is considered to be 1. So, IL is equal to, if it is 1, then the output current is equal to the input current. That is what we have seen in this example. The collector current is equal to the emitter current if alpha is 1. Alpha is the ratio of the collector current to the emitter current. So, if it is 1, then IC is almost equal to IE. So, here also we assume that alpha AC is 1. So, the current IL is equal to II. So, IL is now 10 milliamps. So, what is VL? VL is the load voltage. It is calculated by using Ohm's law. V is equal to IR. So, IL into R, the load resistance. So, IL we know that 10 milliamps into R, it is given as 5 kilo ohms. Substitute here, we will be getting 50 volts. See here, the input voltage is 200 millivolts and output voltage is 50 volts. So, this the voltage is amplified, 200 millivolts is amplified as 50 volts here. So, this is the simple example for the voltage amplification factor, but what is happening for the current? Is the current is amplified? No, the current is same. The input current is always equal to the output current. So, for the common base transistor, we will not get the current amplified, but this is applicable for the voltage amplification only when the transistor must work in the active region. Okay, the voltage amplification factor AV, which has been derived as the amplification factor is defined as the output voltage by the input voltage. So, output voltage is 50 volts and input voltage is 200 millivolts. So, the amplification factor is 250. 250 times the input voltage is amplified at the output, and this is normally 50 to 300 as the ratio, as the voltage amplification factor for the common base transistor, and current amplification is always less than 1, it is of 0.9 or 0.998. So, here in the why this circuit is called as a transistor is the basic amplifying action was produced by transferring the current I from a low to high resistance circuit. When you look at the circuit, it is low resistance, the emitter has low resistance because it is highly doped and it has a more number of electrons to flow. So, the current is maximum. So, when the current is maximum, if there is a low value of resistance. So, this emitter has low resistance when you this part, the emitter and base has low value of resistance when you compare it with the collector base path. And so, the basic amplifying action was produced by transferring a current I from a low to high resistance circuit. The combination of the two terms in italics results in the label transistor, that is transfer plus resistor gives you transistor. Transferring the current from low resistance path to high resistance path is a transistor. And next is common emitter configuration. So, what may be the difference in the circuit when you compare it with the common base? Look at the circuit. Here the emitter is common in between base and collector. So, emitter is grounded, or you can take this as a common terminal, and the base is input terminal, the collector is the output terminal, and this is for NPN transistor. For NPN, again the input junction must be forward biased and the output junction must be reverse biased. So, input junction P is given to the positive terminal, N is given to the negative terminal of the battery. So, it is forward biased, and here it is reverse biased. N is given to a positive terminal and here also N, but it is given to the negative terminal, but we have to see the voltage value. The voltage at the input side must be higher enough to make the transistor to work in the active region, and so the polarity is like this. So, here this N is given to the positive terminal. Simply you have to assume that this potential is lesser than this potential. That is the ultimate meaning for the reverse biased condition here. And this is the symbol of transistor as a common emitter configuration. So, here we know that for NPN transistor, the arrow must be pointing outside, and if an arrow is present in a terminal and that terminal is said to be an emitter terminal. So, emitter is common, base is the input terminal and collector is the output terminal. Always emitter current is equal to the collector current plus the base current. So, here emitter is away, base and collector current are towards the node when you consider this transistor as a node. So, IE is equal to IB plus IC. Similarly, here for a PNP transistor, when you look at the symbol, the arrow marks are opposite because it is a PNP transistor, and also you know that the current direction is a conventional flow of current, it is a hole current which is opposite to the electron flow. So, again if you apply KCL by considering this as a node, IE is equal to IB plus IC. Always it is equal. The emitter will always emit the electrons, collector will always collect the electrons. So, you must remember the equation that IE is equal to IB plus IC. This is the input output characteristics. We know that the input characteristics is drawn for the input parameters. The input current is IB for the common emitter and input voltage is base emitter voltage, for the output voltage constant. Collector emitter voltage is constant. Here for the collector or the output characteristics, it is drawn for the output parameters with the input parameter constant, output current along the y axis and input output voltage along the x axis VCE, that is collector emitter voltage for the fixed IB current. When you recall the output characteristics of common base configuration, here this part is the cutoff region. So, whenever you look into the output characteristics, you have to see where is the cutoff region and saturation region and where is the active region. So, here this is the cutoff region which is shaded, also here in the saturation part it is shaded, and this is the active region in which the transistor will work. So, for the cutoff region, if the current IB is 0 microamps, see the IB current is always measured in microamps because IB is very lightly doped. So, the current is very minimum and it has a larger resistance. So, IB is 0 microamps here. When IB is 0, what is the current at its output? It is not 0, there is a current flow at its output, but when in the case of a common base, when the input current, emitter current is 0, the collector current is 0 in that case. But here if the input current IB is 0 for the common emitter, the collector current is minimum value, that is in millivolts range. This is because of the factor that due to the minority carrier flow, we will see it later. We know that the characteristics is not horizontal because this collector current is affected by this collector emitter voltage. So, it is not horizontal in the active region, but in the common base it is horizontal in the active region. The cutoff region for the common emitter configuration is not as well defined as for the common base configuration. So, this is because this is the equation IC, the collector current is due to the majority carriers as well as the minority carriers. So, this is the majority carrier flow of the collector current alpha IE plus ICBO, which has been seen in the common base configuration itself. And now, instead of IE, if you replace it with IC plus IB and rearranging, you will be getting this equation alpha IB by 1 minus alpha plus ICBO by 1 minus alpha. IB is the input current, ICBO is the collector to base current with emitter open. This is the relationship between the output current with respect to the input as well as the input current as well as the minority carriers at the collector terminal. So, if we consider the case discussed where IB is 0 amps, that is what we have discussed in the output characteristics. If IB is 0, what happens to the collector current? Why it is not 0? It gives you some value. And substitute a typical value of alpha as 0.996 in this equation. IC is equal to alpha IB by 1 minus alpha plus ICBO by 1 minus alpha. If you substitute alpha as 0.996 and IB equal to 0, you will be getting 250 ICBO. IC is equal to 250 ICBO. ICBO is the reverse saturation current, that is leakage current, or you can say it is a minority carrier current flow during the reverse biased condition. So, it is the relation IC is equal to 250 ICBO, and if ICBO is 1 microamps, we know that it is a minority charge, the current due to the minority carriers, and so it is microamps only. So, if it is 1 microamps, if you substitute it in IC equation, IC is equal to 250 ICBO, you will be getting 0.25 milliamps. This is what the current flow present in the output characteristics here. When IB equal to 0 microamps, there is a flow of current at its output. But in the case of common base, when the input current is 0, the output current is also 0. But here this IC is affected by the minority carriers that we have seen in this equation. So, IC is equal to 250 ICBO. ICBO, if you take it as 1 microamps, then it will be 0.25 milliamps is the current flowing in the output characteristics. So, for further you have to deal with ICEO is equal to ICBO by 1 minus alpha. So, what do you mean by ICEO? What is ICBO? It is collector base current with emitter open, which has been seen in common base configuration. Now, it is ICEO, it is common emitter configuration. So, just now we have seen a symbol how you have to draw the common emitter. So, it is common, it is emitter terminal, it is emitter terminal because the arrow presents here, and this is a common emitter. So, it is in between the input terminal base and output terminal collector, and if base is open, the current flow ICEO, this O represents if base is open, what is the current flow through the collector emitter, collector to emitter. So, this is what given in the relationship ICEO is equal to ICBO by 1 minus alpha at the input current 0 microamps, that is base is open. And next is beta, which is beta is the parameter which relates the output current and the input current in common emitter configuration. Similarly, alpha is the parameter which relates output input current in common base. So, here beta in DC mode, it is IC by IB, this is the output current in the common emitter configuration, and IB is the input current in the common emitter configuration. Its value is from 50 to 400, and normally if beta is taken as 200, then the output current is 200 times amplified from the input current, base current. So, this configuration is used as a current amplification, but in common base voltage only amplified, the current is constant when you look at the input and output. Here you can amplify current, you can amplify voltage, you can amplify power also when the transistor is biased in its active region. For AC situations, beta AC is calculated as del IC by del IB, that is the change in the collector current to the change in the base current with the collector emitter voltage constant. So, it has been calculated from the graph, the change in the collector and change in the base current, and they have seen that beta AC as well as beta DC are one and the same in all the points. In each point of the in the characteristics, beta AC and beta DC are one and the same. So, this is what the biasing is given for a common emitter configuration. This is the symbol. Emitter is common to the input terminal and the output terminal, but how will you give the bias? That is what given here. So, base is the arrow pointing towards the bar and emitter is away from the bar, and we know that as per the Kirchhoff's current law, IE is equal to IC plus IB. If it is away, then the collector base current towards must be towards the bar. So, base is towards the bar and collector is towards the bar, and now you have given the current directions, and now you have to give the polarity of the external supply for both the junctions for the device to be in active region. We know that the input must be in forward bias, the output must be in reverse biased. So, this is the NPN transistor. Since the arrow is outward at the emitter terminal, so it is a NPN transistor. So, this is P given to the positive terminal and this is N given to the negative terminal. This is N. So, N is given to the positive terminal and this polarity, which is always lesser than the input terminal's polarity, and so you will be getting a reverse biased condition at its output junction. So, in this way you have to give the bias for the transistor in common emitter configuration. And what is the conclusion in common emitter configuration is, if the transistor is biased in the active region, the transistor can be used as a current amplifier, voltage amplifier as well as the power amplifier. And beta is the current amplification factor which relates the output current to the input current, and if it is AC, then it is change in the output current to the change in the input current. Both beta in both the conditions, that is AC as well as DC conditions, the beta will be almost equal. In the case of common base configuration, the transistor is used only for the voltage amplification, not for the current amplification. The current amplification factor alpha is equal to 1 always, almost equal to 1 for the common base configuration. Next we will see common collector configuration. Common collector, the collector terminal is common to the input terminal as well as the output terminal. See this, in this picture it is clearly given. This is the PNP transistor. Here collector is common to base and the emitter. So, here this is the base is the input terminal. Since it is a N type, it is given to the negative polarity, and this is P type given to the positive polarity for the input junction to be forward biased and for the output junction to be reverse biased. If you look at the common emitter circuit, just you are reversing this polarity and reversing the terminal, that is all. That is the difference between the common emitter and common collector. See here the input is base in both the configurations. Only thing is, for common emitter, emitter is common, output terminal is collector. For common collector, collector is common, output terminal is emitter. And so, here if the collector is taken the positive terminal, again there also in the common collector also the voltage is reversed here. The emitter is taken the positive terminal of the battery. This is the difference in circuit diagram between the common collector and the common emitter configuration, and this is the symbol. So, here for PNP the arrow is given towards the bar and it is a emitter terminal, and here this is the collector terminal common to the input and output terminals base and emitter. For NPN the arrow is away from the bar. So, this is the replacement of the transistor when it is in common collector configuration. Normally we will use this collector terminal common to the input and output, but here it is grounded. It is taken at the reference level or it is grounded here, and the output is taken across the emitter terminal by adding a load resistance at the emitter terminal. So, this common collector configuration has the speciality that it can be acted as a buffer, because the input side resistance will be very high, because the base is the input terminal, and so the input resistance is very high, the output resistance is very low. So, you can connect this, you can use this configuration as a buffer for all practical purposes. And the characteristics are mostly one and the same when you compare it with the common emitter configuration. These are the limits of operation. The power dissipation must be equal to VCE IC. The IC max is 50 milliamps and VCEO is 20 volts only, and the common collector emitter current with base open must be less than or equal to IC maximum, and this is for common base characteristics. The power dissipated must be equal to the collector base voltage, the product of the collector base voltage and the collector current. Summary: we have seen different configurations of the transistor as common base, common emitter and common collector, and we have also seen the input output characteristics, and in the output characteristics we have seen when the transistor will be worked as a voltage amplifier, current amplifier and power amplifier, and when the transistor is used as a buffer. So, common collector is used as a buffer, common emitter is used for the amplification of current, voltage and power, and common base is used for voltage amplification only. And here are some of the questions. What happens when both the junctions are forward biased? Explain in brief about the amplification in common base configuration. Give the relationship between beta and alpha. These are the references. Thank you.